Toothpaste seems to challenge the behavior we usually expect from the simplest fluids. If it were like water, it would immediately drip off your toothbrush before you could use it. But if it were a rigid solid, you wouldn't even be able to squeeze it out of the tube. And yet, it does something strange. It remains stable when you want it to, and begins to flow exactly when you apply pressure. So the real question is not just what toothpaste is. The real question is, how is it possible to design a material that behaves like a solid and a liquid at the same time? And once you understand this, you will start noticing these kinds of materials everywhere, even in some of the most important engineering projects in the world. When you squeeze toothpaste onto a toothbrush, something very particular happens. It does not spread out, it does not collapse, it does not flatten like a common liquid. It forms a smooth ribbon that keeps its shape for several seconds. But the moment you squeeze the tube, the opposite happens. The toothpaste flows with surprising ease through a very small opening. That combination is uncommon in simple fluids. Most materials tend to behave in a much simpler way. They either resist deformation like solids, or they flow continuously like fluids. Solids strongly resist deformation. If you try to push them, they tend to maintain their original shape. Fluids, on the other hand, deform continuously when a shear stress is applied. Shear stress is a force per unit area that acts parallel to a surface and attempts to slide one layer of material relative to another. Water, oil, or even air will continue flowing as long as that stress is applied. Toothpaste seems to challenge that logic. It does not fully fit into either category, and to understand why, we need to step back and see how scientists classify fluids. In physics and engineering, there is an extremely important category of fluids: Newtonian fluids. In a sense, they are the simplest fluids that exist. A Newtonian fluid is one in which viscosity, that is, resistance to flow, may change with temperature or pressure, but does not change with time or with how fast you try to deform it. Water is the classic example. There's a proportional relationship between the applied shear stress and the deformation rate of the fluid. In simple terms, if you double the shear stress, the deformation rate also doubles. Many common fluids behave this way, including water, alcohol, and most light oils. These fluids are mathematically elegant, predictable, and relatively easy to model, but nature is not always that simple. There is an entire class of materials that does not follow this simple behavior. They are called non-Newtonian fluids. A non-Newtonian fluid is a fluid whose viscosity changes depending on how you manipulate it. It may depend on the applied stress, the deformation rate, or even time. Some become more fluid when stirred, others become thicker, and some can behave like solids under sudden impacts. A very surprising example is a mixture of cornstarch and water. If you hit it quickly, it can behave similarly to a solid. But if you manipulate it gently, it flows like a liquid. Another everyday example is ketchup. When you try to pour it without shaking, it can behave like a highly viscous or yield stress material. But just shake the bottle, and suddenly it flows. Shampoo, mayonnaise, paint, and many cosmetic products also belong to this category. But toothpaste belongs to an even more interesting subgroup, one that explains exactly why it remains stable on your toothbrush. Toothpaste is usually classified as a yield stress fluid. And here appears an idea that seems simple, but completely changed how engineers design many materials. A yield stress fluid presents an approximate threshold above which flow becomes significant. In other words, the material must exceed an approximate minimum stress for movement to become noticeable. Below that threshold, the material may behave similarly to a solid or flow extremely slowly. It can resist small forces without visibly deforming. But when the stress exceeds that limit, the material begins to flow. This behavior describes toothpaste quite well. To mathematically describe this behavior, scientists often use a model called the Herschel-Bulkley model. The Herschel-Bulkley model describes the relationship between applied stress and deformation rate using the following equation. Tau equals tau sub y plus k times gamma dot raised to the power n, where tau represents the applied shear stress. Tau sub y is the yield stress. K is the consistency index of the material. Gamma dot is the deformation rate. N is the flow behavior index. First, the yield stress defines approximately the threshold above which material motion becomes significant. Second, the consistency index describes how resistant the material is to flow once it begins moving. Third, the flow behavior index indicates how viscosity changes as deformation increases. This model helps describe and approximate why toothpaste can easily come out when you squeeze the tube but still remain stable on the toothbrush. Toothpaste is not a simple substance. It is a complex mixture of solid particles suspended in a structured liquid phase. A typical toothpaste contains microscopic abrasives, binders, water, humectants, detergents, and various additives. These particles can form an internal three-dimensional structure that helps keep the material cohesive. When sufficient stress is applied, this structure partially breaks, allowing the material to flow. When the stress disappears, the structure can rebuild partially or progressively, largely restoring the stability of the material. This reversible behavior is characteristic of many yield stress materials. What is fascinating is that toothpaste is only one of the most visible examples of this phenomenon. Fresh concrete behaves in a surprisingly similar way. It must flow when poured into molds, but it must also remain stable enough to avoid excessive deformation under its own weight. Paint is carefully designed to spread evenly without dripping. Many foods, including sauces, creams, and spreads, rely on similar physical principles. But this behavior also appears in some of the largest engineering projects on the planet. An extraordinary example is bentonite. Bentonite is an extremely fine natural clay that generally forms from the alteration of volcanic materials, often volcanic ash. It is mainly composed of minerals from the smectite group, especially montmorillonite. What makes this clay so special is its ability to hydrate when it comes into contact with water and expand, forming suspensions with very particular properties. For this reason, bentonite has a huge variety of industrial applications. It is used in oil drilling muds to transport rock fragments to the surface and stabilize well walls. It is also used in geotechnical excavations, pile construction, tunnels, and impermeable barriers, where it helps stabilize excavation walls through hydrostatic pressure and the formation of an impermeable filter. The physics behind toothpaste turns out to be fundamental in many industries. Toothpaste may seem like a trivial object, but it is a surprising example of engineering and material science working perfectly. It can behave similarly to a solid when at rest or under small stresses. It can flow like a liquid when subjected to sufficiently large stresses. And this carefully designed balance appears in countless systems that we use without even noticing. From construction materials to foods, from geotechnical drilling to cosmetic products, these materials are everywhere. Sometimes the most sophisticated physics is not in futuristic laboratories. It is found in everyday objects that we use every morning, even in something as simple as toothpaste. If you found this video interesting, consider subscribing. It really helps the channel grow and allows me to create more content like this.